Good job for doing it. What you just shoot? Like shooting wild in the air.
All right, so we're going to do a few more examples with projections. One thing that I have seen people in the past get mixed up is how this thing is written and what exactly it means. Pretty sure I wrote this last time. It's written kind of like a log has a subscript. You can do like log base 5 of something. It's written similar to that. So the vector that we are projecting onto is the subscript. So if we see it like this, we're projecting onto V. So this is the vector projection of U onto V. And I posted a couple of videos about projections that a couple of you guys watched, or at least clicked on. Can't tell if you watched the whole thing. So there's just a formula for it, but I'm also going to draw a picture to try to give it a little bit more meaning. So the vector projection of U onto V, we do U dot V over the magnitude of V squared, and that value is a scalar. Dot product gives back a scalar, magnitude gives back a scalar, and we're just setting them up in a fraction. Okay, so this entire value here is just a scalar. And since we're wanting to project onto V, our answer is in the same direction as V. So this is the scalar that tells us how to stretch or shrink V so that we can use it to help make our U vector. There is another very similar concept, and that is the scalar projection. So this is a vector projection. The answer is a vector. We may just want to know how long that vector is. How long the answer is, and that would be the scalar projection. So it just gives you the scalar, but not the full scalar that's in the parentheses. Because one of these magnitudes, technically, if we pull it out with the V, one of them is going to shrink V down to a unit vector, and then the other one will then readjust it to the correct length. So remember, a unit vector, and I hate to use U again, is V over magnitude V. That's our formula for finding a unit vector. So the magnitude V squared in the bottom, that means there's two of them. We could scoot one of them outside with the V and say that's shrinking V down to 1 unit, and then whatever is left in the parenthesis represents how we're going to make V the appropriate length to use. So really the scalar projection is just U dot V over magnitude of V. It's not squared because one of those actually has the purpose of shrinking V down to a unit vector. And then the other one is used in the calculation of how long we want the new vector to be. And this is called the scalar projection. And the scalar projection is just the magnitude of the vector projection. We might not care what direction it's pointing in, we just want to know what the value is. And we're going to see a lot of these same formulas come up in various other sections. We're going to start doing distances between different like three-dimensional entities. This formula is going to come back up as a distance formula. We're also going to have, I know I've talked about it several times, components of acceleration, where we break acceleration into two vectors, one that's in the direction of motion and one that's perpendicular to motion. We're going to see this exact same formula come up there as well. So we did one quick example last time before the end of class. I just wanted to go through a couple more. So if we've got vector A, I think the one we did last time was two-dimensional, so I'm going to do three-dimensional this time. Vector A is 2, 5, negative 3. Vector B is negative 1, 2, 1. We are going to find the scalar of B onto A and also the vector projection of B onto A. So which vector is in which position is really important. We're going to dot them in the numerator, and that doesn't matter which one is which. But only one of them goes in the denominator. So this is what we are going on to, which means we want our answer to be in that direction, which means that vector is going to be the one that we're doing a scalar multiple of. Okay? So for vector projection, I'm ultimately going to be doing some scalar of vector A. Yes. In the top, we dot them. In the bottom, you've got a choice of A or B, and which one you put there is going to make a big difference. Remember that it's the same as the vector on the outside, because technically it's squared, and one of them can be scooted to the outside to turn it into a unit vector. So if I've got A on the outside, then I need magnitude of A squared on the inside. And then up here, for the scalar, it's just the dot product over the magnitude. We don't need to square the magnitude because one of those is serving the purpose of turning A into a unit vector. The other one is helping us to stretch it back out for use in our projection problem. So you remember how to do the dot product?
You multiply like.
Multiply like terms or like components, and then add the results. Yep. So we're going to be doing 2 times negative 1, 5 times 2, and negative 3 times 1. We're going to do those three products and then add them together. So this is negative 2 plus 10 plus negative 3. In the bottom, we want the magnitude of A. And magnitude is like the distance formula. Distance from 0, 0, 0 out to that point.
4, 25,
Not 3.
9.
2 squared plus 5 squared plus negative 3 squared, right? It would be 9. Yep, 38. So we got radical 38 in the bottom, and we got 5 in the top.
On the homework, I think it was taken that answer. I don't think you had.
Didn't have to rationalize. Good. So the only thing different with the vector projection is that we're going to square the magnitude, and then we're going to use that fraction to distribute into the A vector. to change the length of vector A. Because A is the proper direction, it's just not the proper length right now. And I'll show you again the two-dimensional picture of what I need. So we've already done A dot B. That was 5. We've already done the magnitude of A. It was radical 38. This time, though, we square it. And all that's going to do is cancel off the square root. And we're going to think of this as a scalar multiple on vector A. So we're going to do 5/38 times vector A, which is 2, 5, negative 3. So that comes out to be 10 over 38, which simplifies to 5/19. 25 over 38. And negative 15 over 38. Now, if we went ahead and found the magnitude of that vector projection, what is it going to be? We already have the answer. It's going to have a 38 in it, but that's not the final answer. 5 over square root 38. It's the exact same thing as the scalar projection. And let me actually throw some absolute values around there, because the scalar projection could possibly turn the vector around and make it point in the opposite direction. So the absolute value for the scalar is the magnitude of the projection. So if we were to go and do our magnitude formula on that, it would come out 5 over square root 38. You think I can prove it? Don't challenge me and then, The question is, can you? With the radicals in there, though? Yeah. No way. What's 19 squared? No. It's 190 and 181.
361.
361?
360. 190 and 180 is.
Okay.
Oh, yeah, it is. I'm sitting here looking at it.
25 squared is 625. What's 38 squared?
Why don't you know that? You should know that. 1444.
But you guys already have your calculators out. I can figure it out.
Yeah, I think you keep going.
I'm not stopping. What do I need to multiply by to turn 361 into 1444? Is it 19? 4. It's missing 2 factors of 2, because 19 and 38 are off by a factor of 2, and then we squared them. So we're going to multiply top and bottom by 4 here, so that's 100 over 1444. So now they've all got like denominators, we can add the numerators. 950.
Square root 950 over 38.
Do you guys know how to simplify square roots in your calculator? I've showed you.
You said square root 950.
In your y equals, you can do 950 over x squared. And look in the table. And whatever's in the X column is what comes out, whatever's in the Y column is what stays in the square root.
5 and 5 is an outside, 38 is an inside.
If we were to rationalize this guy over here, oh, there's supposed to be a little thingy. If we rationalize that, you'll get 5 radical 38 over 38. So the only thing difference here is our answer is rationalized. This is exactly the same thing. Because Adam challenged me.
But actually, I was just trying to waste time.
I know. And I'm a sucker for it.
I knew if I said that, I'd probably waste like 5 minutes. So yeah, I was like, let's do it. What were you trying to do? That she could do
That
it.
the magnitude of the projection is equal to the
You don't have
scalar.
to give in the peer pressure.
No, 'cause you-
What I did
she's always
here,
making pot.
what,
Oh, this is recording.
the magnitude of the projection just comes out to be the absolute value of the scalar.
Why'd you do all that?
Because Adam asked me to prove it.
No, I told her she couldn't.
This technically is not a proof, though.
No. What's a Brenner difference?
Proofs require you to use arbitrary variables. So if I were to go through this whole process and have my scalar as with just letters in it, and then the magnitude of my, he's just stalling me.
No, I'm not. Yeah, I was just laughing at someone.
And then go through the whole magnitude formula with just letters, and then prove it with that the letters match up. That means I could replace the letters with any number, and it's always going to be true. So technically, all I've shown is one case where it works. But to do a proof, you actually have to do it with arbitrary variables and show that it's going to work every time.
So you didn't prove wrong. I'm just kidding.
Technically, maybe I'll assign it for homework.
No, it's not my fault. Oh, yeah, sorry, proof.
So these are not the A and B vector, but just as a reminder. Let's say this is the A and this is the B. I don't like how long that is. Fox? The vector projection, what did we do? A onto B or B onto A? We did B onto A. That means I want to connect B to A with a line that is perpendicular to A. The vector that we end up with on A, that is the vector projection, this right here. That is the projection of B onto A.
The way in the video they explained, the guy explained it was like it feels like sunlight and lets
It's like a shadow.
yeah, the shadow.
The shadow is always here at the tip of B. So if you were to look at the shadow of B that it creates on A, the shadow would be that long. So 5 over, what's wrong? We ready to just be done with this? You were insulting me? At least you're honest about it.
I said I was scared for that song. It's not right. It's like a boat. Squash.
Does look like a fat old squash spider. It's got vector S and vector T. I want you guys to try this one. That is an excellent question. We need to know that because it makes a difference. Okay, so we're going to do the projection of S onto T. The one that's written as the subscript is the one that we're going on to, which means our final answer is just a scalar multiple of T, which means what goes in the denominator of our scalar? S or T? T. Because one of those we can think of as coming out with the vector T and turning it into a unit vector. So whatever we're going on to, that's the one in the denominator with the magnitude squared, and it's also the one out to the side that we're doing the scalar multiple of. So I didn't ask you for the scalar projection, just the vector projection. Nope. What do your z components multiplied together make? It's okay.
I did the right thing for the first two.
Yes.
And I guess my brain just thought, oh.
And it's going to get even worse when we get to cross product, because you're going to be doing the same exact thing again.
Well, for the cross product, I just use this formula.
Okay.
Because it's like AX times BZ minus da 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 plus same thing, just random combinations.
Yes.
Is that what we're gonna use?
It's not random though. I'll
It's
show
not
you.
random,
I'm going to show you the
like,
pattern.
so
Or didn't I show you the pattern? No, it might have been Jared that I showed the pattern to. There is just this big random long formula, but there is a pattern to it. And there's another way to do it where you don't have to memorize the formula at all if you do a determinant of a 3x3 matrix. For the projection of S onto T, what do we get for the dot product? 2. Because we're doing -1 times 4, and then 3 times 2, and then 0 times -2. So -4 plus 6 plus 0, we get 2. For S onto T, we want the magnitude of T squared in the bottom. Yes, these are a little bit nicer. So for the magnitude of T, we're going to do 4 squared plus 2 squared plus -2 squared. The magnitude is radical 24, but the vector projection formula tells us to square that, so we use regular 24. And then this is how we are going to scale T to make our shadow. So we're really going to do a 12th multiplied into the T. So you should get, if you simplify, 1/3, 1/6, -1/6. All right, projection of T onto S, which is going to be a completely different answer. There's only one piece in the whole formula that's going to stay the same, and which one's that? The dot product. We still do the exact same dot product in the numerator. But our other two pieces are going to be different, because now we're doing magnitude of which one in the bottom? S. We're going to do magnitude of S squared in the bottom, and that's going to give us a scalar to distribute into vector S. What's the magnitude of vector S? square root 10, and then we're gonna square it. So we get 2/10 or a fifth. So this is telling me to get my projection, I need to only use 1/5 of vector S. Vector S right now is way too long. We're gonna shrink it down to just a fifth of its normal size. So if I multiply through my S vector by a fifth, I get -1/5, 3/5, and then 0 still. 0 times anything is 0. So the projection of S onto T, projection of T onto S, two completely different answers. So if that's our S and our T, and I shine a light over here to do S onto T, I'm going to connect it to T with a perfectly perpendicular line to T. It's always got to hit T perpendicular. And that's almost perpendicular right now. So it ends up being really small. Where it hits, that is our projection. If I do the shadow of T onto S, and I think of the sunlight as being over here, that is not perpendicular. That's a little better. It's better than the last one. There is, I did both of them. That is the vector projection of T onto S.
Oh, it is a box. I see it.
I do see it on this one now.
It's like yellow liquid squirting on its own.
This is his nose, these are his eyes, those are his ears.
It's two giant spiders.
They're attacking from both sides. Doesn't the Air Force symbol look kind of like that? Yeah.
Chair force.
Questions about projections? When I was in college, my teacher taught it terribly. Didn't explain any of it, didn't talk about the shadow, didn't talk about a scalar multiple of one vector to the other. They just kind of threw the formula at us and said, you need to know this formula. This is what it's called. So it's like, that was one of my least favorite things in Calculus 3 because it made no sense to me whatsoever. So I had to like figure it out all on my own.
Here's like box everything.
So every wrong that was perpetrated on me as a college student, I try to make it right to my students. And this is one of the major things from Calculus 3 that I was very bitter about. We okay with projections? Okay. So like Arturo said, he watched the videos that I posted. It's like a shadow.
I couldn't get in the word because my school blocked YouTube.
Yeah.
So we still try to do that.
We used to block YouTube here, and then we told them how much we use it,
Exactly.
and they took it off.
But they don't block all of it, but some videos are blocked. The ones I use are always blocked.
It's 3 o'clock.
No, man.
All right, so I'm going to show you the cross product formula, which most of us, it sounds like I already know if we took physics. I do it very differently. I don't just memorize this big random formula.
Can we do that?
You can, yeah, because all I'm going to ask you to do is tell me what the cross product is. So however you do it is completely up to you.
Because we get a note card, so.
So would this be section like before?
Uh-huh. So when we did dot product, we said we could also call it scalar product because the answer is a scalar. Cross product is also sometimes called vector product because the answer is a vector. And the reason we do vector product is we're looking for something that was perpendicular to the two vectors that we put into it. So the cross product will always yield a vector that is perpendicular or orthogonal or normal. All three of those words pretty much mean the same thing. To the two vectors you put into the calculation. We can only do this in three-dimensional space. So any two vectors can define a plane. We can draw a plane through just two vectors. But once we want something that's perpendicular to both of them, we have to shoot out of that plane in a different direction, which is going to be a third dimension. So we only do vector projections, or excuse me, vector products, cross products in 3 dimensions. So that U cross V, you got to think of it as being in 3 dimensions. If we started with U and with V, U is going straight up, V is like going back into the board. U cross V, am I going in the right direction? Yeah. U cross V is going to be perpendicular to U, and it's also going to be perpendicular to V. It makes 90-degree corners with both of them, but it does it in 2 different planes. So there's a UV plane that's kind of standing up and coming out at us, and then, the U and U cross V plane. Sorry, I keep jumbling. There's a plane defined by U and U cross V, and it's a flat plane standing up and kind of heading towards Eason and Joa. And then there's a V and U cross V plane, which is flat. So it makes, yes. There is another vector that's perpendicular to both of them, and I didn't use that one purposely, because we do all our math in this class in the right-handed system, okay? And the way that I like to describe a right-handed system with cross products, the order that you do a cross product in is going to make a difference, because if you switch them, you'll get a different answer. So if I want to do U cross V, I'm going to start I am pointing in the wrong direction, aren't I? I was doing it with my left hand this whole time. I'm sitting here doing it with my left hand because I'm writing with my right hand. I'm not going to redraw my picture, but I'm going to relabel them. Okay. I'm going to keep my vectors the same. The way that a right-handed system works is that the cross product will be the direction your thumb points. If you use your right hand and you start at the first vector and curl it towards the second vector. Start at the first vector and curl it towards the second vector. Your thumb will point in the direction of the cross product. So you might have to do this then. So I need to make sure that when I curl from U to V, so I'm going to say this one is U, and this one is V, and then this one is going to be U cross V in a right-handed system. So if you start at U and you curl towards V, your thumb points up. That's why U cross V is up. Start at U, curl it towards V, thumb's pointing up.
But
Start
it's
with-
like that way. Like,
You're moving your hand. Start with the start with the outside of your palm resting parallel to you. And now just curl your fingers in the direction of V.
I had this part.
Okay, yeah, we want the outside of your palm and curl it towards V. Now, a left-handed system, in order to do that, you would be underneath U in order to have the outside of your palm parallel to you. And then when you curl it towards V, your thumb would point down. So in a left-handed system, U cross V would point down. In a right-handed system, U cross V points up.
So if you're left-handed, you're screwed.
If you're left-handed, you're screwed. You got to learn to do this with your right hand.
Left hands matter.
Left hands matter. Not in Calculus 3.
Right hand, I still can't do this.
All right, let's take a vote.
No.
Is U cross V pointing at us or pointing back? If U and V are flat on the board,
I know, that's not what I guess.
No, it's put that way.
Arturo says it's pointing in.
I think it's, I don't even understand how this works.
My thumb is pointing.
Use your right hand. Start it at U.
What do you mean by started?
Yeah, that's why I still don't get that.
Make it slant just like U slants.
Okay, my thumb
Instead of looking like this.
or my hand?
Your right hand.
Okay, and then
Curl.
So U is right here with my right hand.
yeah.
Can you do it standing up facing the board?
Yes. Yeah. Yeah. You get up there and
Yes.
do that. I'm gonna break my hand trying to do this. Okay. Okay.
But then I'm facing this.
I thought you said you did this side.
But you're not touching V.
You want this on the U, so technically in three-dimensional space I would be behind it.
Well, then you can do it like this then.
So this is why Mr. Nash is always like breaking his arms.
Yes. Yes.
Why can't you do it like this? Like, you know,
Because to curl towards V, you're gonna have to go all the way around this way.
oh, okay.
And when we do the angle between U and V,
Okay,
it always
gotcha.
does the smaller one.
Okay.
So it's the smaller angle.
I might just use my right left hand and erase my left hand and say it's an opposite direction as that. Just so I don't have to
Yeah,
use
it-
weird-
And that's actually the rule. They're exactly opposite direction.
Yeah.
if you do U cross V or V cross U, or if you switch between right hand and left hand. So starting at U,
Just doing it
curling towards V,
It's like easier than.
my thumb's gonna point into the board.
So if I start at V.
And then,
If you start at V and curl to U, it's gonna point out at
My
us.
hand switches to this side.
Yes.
Why?
there's gotta be a constant in here somewhere. It's just.
How do I know which side
It
my
is
hand is?
That's a good question, to be honest.
You want it open towards the other vector. You want your hand open towards the other vector.
Okay, that makes more sense.
Does that help?
A little bit.
A lot.
Okay. So here's U. It's open towards V because I have to curl towards V. If we did V cross U, it's open this way because this is the way I'm going to curl. It is not very important. We spent a lot of time on that. It's not important at all. It is important, but so the answer is, Arturo is right. This one, U cross V, is going to go into the board.
Next to home. He's got English.
So those are both supposed to be 90-degree corners. The UV is going into the board. It's perpendicular to both U and V, but on different planes. All right, so it's time to go. I'm going to tell you the 3x3 matrix real fast, and then we're leaving, okay? So to calculate U cross V, what I do, so that I don't have to remember the formula, but I will show you the formula and I'll show you the pattern in the formula, is I set up a 3x3 matrix with IJK in the top row. And the reason IJK are in there is because I need them in my answer, because a cross product can also be called a vector product. The answer is a vector. Whatever vector is first in your cross product, its components go in the next row. And then whatever vector is second goes in the last row. So I've got IJK, the components for U, the components for V. And we need to figure out what the determinant of this matrix is, and we can't do it in our calculator because they're not all numbers. The IJK are like variables. So what we're going to do is called cofactor expansion, and we're going to turn this 3x3 matrix into 3 2x2 matrices. The way that we do that, I'm going to expand this across my first row. So I'm going to take my I value and just write it as a coefficient. And now you're going to cover up, and I'm going to undo this in a second, cover up I's column and I's row. And you'll be left with 4 values that make up a 2x2 matrix. Okay, so next to the I, I'm going to write the 2x2 matrix U2, U3, V2, V3. We had to cover up I's column and I's row to get that. See what's left over. And then we move on to, I'm going to undo that because I don't want them to stay covered up for the next step. Oh, it's going to undo these.
So then J is going to be.
Let me do it in a different color. So for J, it's a rule of linear algebra that when you do the J, you change to subtraction. It's positive, negative, positive. And if you cover up J's row and J's column,
U3, V3.
yep, you got U1, U3, V1, V3 left over. And then for K, you're going to go back to plus again. So plus K, cover up K's row and K's column, U1, U2, V1, V2. So a 2 by 2 matrix we can easily do. To do the determinant of a 2 by 2 matrix, you do the product on the major diagonal, and then you subtract the product on the minor diagonal. So I've got one more step till I have like the full formula that you guys are used to memorizing in physics. So this ends up as I times U2 V3, that's my major diagonal here, U2 V3, minus U3 V2. That's how we do a determinant of a 2 by 2 matrix. And then I've got minus J, major diagonal is U1 V3, and then the other one is U3 V1.
It's a lot easier that you explain it that.
Some big formula with 12 pieces in it. Yeah.
I saw that when you first wrote the book, I just blanked out.
I'm done today. Today is over.
Yeah, because he expects us to know it, and we've never seen it before.
For K, major diagonal is U1 V2. Minor diagonal is U2 V1. There is a major pattern in this formula that can help you memorize it if you just want to do the formula. And it's even better than that. So the I component is usually in what position in a vector? First, second, or third? First position, okay? I is the first position in the vector. So the numbers or the components we're going to use from our vectors are the other two. So the 2 and the 3. So I is the first, and then we see the second and the thirds. The vector that comes first in the product always is going to use the lower one first. So because I'm doing my I component, which is the first vector, I'm going to use the second and third components for the calculation. Whichever vector comes first is going to take on the 2 first, and then the flip-flop. So it's 2, 3, 3, 2. J is what position? Which is second position. So notice in the parentheses, I don't see any 2s. It's 1, 3, 3, 1. And U gets the 1 first because U comes first in my product here. The order matters because if we switch the order of that subtraction, it'll come out exact opposite value. And then K is the third component. So notice in the parentheses, there's no 3s. It's 1s and 2s. And U starts with the 1, the lower value, and then they flip-flop. So there is a pattern between all of it. But it's also just a determinant of a 3 by 3 matrix.
And so, let's say they asked you to do, what they asked you to do in the homework was to find first the unit U times V, and then V times U, which is basically just a sign switch.
Yes, it would just be a sign switch. If you switch the order of cross product, it just switches the sign on everything. Yep. What we're doing is we're finding the determinant for the matrix. And a determinant is like it's some sort of quantitative value that you can assign to the matrix. But because we've got a row of letters, it doesn't actually come out to be a single value. It comes out as a combination of those letters, the I, J, K. So we're just finding its determinant. We're just doing this one example, and then we're leaving. I know it's 3:20 already. So we want to do U cross V. U is 5, -10, V is -342. So if you've already gotten the formula memorized, that's perfectly fine. If I had to come up with a formula without doing the 3x3, I could. I'm just so used to always setting up the 3x3 matrix. I prefer to do it that way. So in this cross product, U is first, which means I'm going to write my U components above my V components, which is important because it's going to be a difference in how we subtract. So then my V components are on the bottom row, -342. And we're going to figure out the determinant of that matrix with cofactor expansion. So for the I, I'm going to cross off I's row and I's column. And we do the major diagonal, which starts in the top left corner. Just like when you start reading a book, you start in the top left corner. So matrices are the same way. The major diagonal starts in the top left corner. So we do -1 times 2 is what? -2. And we subtract from that the product on the minor diagonal, which is 0. We've got 4 times 0 is 0. Oh, yeah. Okay, got rid of the red. Now we're going to do the J. So we cross off J's row and J's column. And we switch to J, you switch to subtraction. And we're left with, that is our major diagonal, and that one is our minor diagonal. So the product on the major diagonal is what? 10. We've got 5 times 2 is 10. And on the minor diagonal, 0, because we've got -3 times 0. And then we switch to K, and we're back to plus. If you cross off K's row and K's column, we'll be left with a 2 by 2 that has a major diagonal of what value? 20. And then we subtract the product of the minor diagonal, which is 3. So we've got -2i minus 10j plus 17k. That's our cross product.
In other words,
Or you could, yeah, you could write it in brackets also. -2, -10, 17.
So let's say that, I came out to be 0.
Mhm.
Do you have to put 0i or just?
You could if you wanted to, in case you needed. Our goal is going to ultimately to be do something else with this vector. So we might want to see that there's a 0 there for further calculations. We definitely would have to put a 0 in over here because we need all 3 positions identified. You could leave the 0i off and it would still be correct.
If you just put I.
Then that means 1i. So either leave it off or put a 0 coefficient.
Because in the homework, they gave you 1 with 3, and then they didn't have an I, and they just have a J. And that threw me off.
So you don't have to necessarily copy this down. You guys can pack up if you want to. But if we had vector A, not plus, was equal to 2j minus 3k, and then vector B was 5i plus 9k, we would have to recognize which ones are missing and put in coefficients of 0 when we set up our matrix. No, that would be along the lines of dot product, when you multiply corresponding components. I want to write these out with their I, J, and K components. So what's the I component in A? 0. So when I set up my A cross B, it's going to be 0, 2, -3. And when I set up my B, 5, 0, 9, because the J is missing, which means there are 0 J's. Yeah, so if anything's missing, you put a 0 in that spot, because you need all 3 in order to do the cross product.
So what does the cross product represent? Like, what is it?
The cross product represents the area of the parallelogram that's created between A and B. So here's vector A. Here's vector B. Remember how we did parallelogram method?
So it's the area then?
If we take the magnitude of the cross product, it's the area of that parallelogram.
No, that's why they asked that.
Cross B with an A would be.
It'll just come out an opposite sign. All the coefficients will have opposite signs, but the magnitude would still be the same. So the area inside here is the magnitude of the cross product.
So A cross B would be going into the board.
A cross B would be going into the board. Perfect.
Like the argument more than 16.
Yes. And this would also be the magnitude of B cross A, because technically those would be parallel vectors just pointing in opposite directions. They'd have this exact same magnitude. They're just, one's pointing into the board, one's pointing out of the board. And B cross A would come out at us. A cross B would go in. So that's one of the things we do with the cross products. We can do area of that parallelogram. But there's also a lot more stuff. Did everybody finish their project? Yes? Okay. Homework is not due tonight because we're still not done with cross product. And that homework goes through cross product. I'm sorry, Arturo. I know, but you busted your butt trying to do it.
Yeah, I thought it was due today. That's why I did it.
Yeah. I'm going to change it since we didn't finish cross product yet.
I figured it wouldn't be due. Whoa, you're gonna change it.
Change the due date.
Okay, I was like, they're gonna add different problems. I was like,
No, I'll change the due date since we're not done with cross products.
You should have some more problems. Double it.
Shut up. But I'm getting a 50.